Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about aliphatic nucleophilic substitutions. You know my friends, aliphatic nucleophilic substitution reactions are very important and it is very helpful to understand chemistry. So, you know aliphatic nucleophilic substitution and types. Second, I will discuss like mechanisms, SN2 mechanisms, evidence for the SN2 mechanism, SN1 mechanism, evidence for the SN1 mechanism, the set mechanism, single electron transfer, the SNI mechanism, mixed SN1 and SN2 mechanisms, nucleophilic substitution at an allylic carbon, nucleophilic substitution at an aliphatic trigonal, and carbon nucleophilic substitution at phenolic carbon. So all these topics are very important for your exams. So I will discuss one by one and you make your note. Now, aliphatic nucleophilic substitutions. Substitution means what? Replacement of an atom or group of atom by any other atom or group of atom. What is nucleophile? At least one unshared pair of electrons, Lewis base, attracted towards positively charged species, may be neutral or negatively charged. So, attracted toward positively charged species, may be neutral or negatively charged. Examples: chloride, bromide, iodide, cyanide, hydroxide, ammonia, amines, water, and alcohol. Look at general reactions. Substrate, nucleophile, substituted product, and living group. Nucleophile, Y, may be neutral or negatively charged. Substrate may be neutral or positively charged. So types of nucleophilic aliphatic substitution reaction. Type 1, you can see RHI converted into ROH. Second types are I converted into RN trimethyl, which is look like salt. Third, RN Me3, it is react with the OH minus ROH. And type 4, again react with H2S and SH2. So look at here SN2 reaction mechanism. You know about the SN2 from 10 plus 2. SN2 mechanism, you know, substitution nucleophilic bimolecular, backside attack, single step, direct displacement, no intermediate formation, inversion of configuration. The energy necessary to break the Cl bond is supplied by simultaneous formations of the carbon nucleophile bonds and generally yield single products. So these are very important points related to SN2 reaction. Here L living groups and Nu minus attacking nucleophile. Now evidence for the SN2 mechanism. You see the kinetics, rate expressions, K substrate and nucleophile, it depends on both. If large excess of nucleophile is present, that is solvolysis, that is rate is equal to K substrates, and such kinetics are called pseudo first order. So SN2 energy diagrams, you can see SN2 reaction is one step reaction and transition state is highest in energy. Now stereochemistry, you know the transition state of SN2 reaction has a planar arrangement of carbon atom and the remaining three groups. Occurs with the inversions of chiral center called Walden inversions. You can see here. So no substitution at bridge head carbon. Why? Not be able to react by this mechanism since the nucleophile cannot approach from the rear. Requirement for the SN2. You know the SN2 mechanism requires the backside attack by the nucleophile, inversion of configuration and coplanarity of three no reacting groups in the transition state. The reasons: prevent at the bridge head carbon due to rigid cage-like structure, so no reaction. Now SN1 mechanism. You know the SN1 mechanism, nucleophilic substitution nucleophilic unimolecular. This is two steps process. The first step is a slow ionization of the substrate and the rate determining step. The second is a rapid lineation between the intermediate carbonations and the nucleophile. The ionization of a living group to form the carbocation is always assisted by the solvent, since the energy necessary to break the bond is largely recovered by solvation of cation and the living groups. So evidence for the SN1 mechanisms. Kinetics, you can see first order reaction following the rate law. Rate is equal to KRX. So solvent is necessary to assist in the process of ionization. It does not enter the rate expression because it is present in large excess. So SN1 energy diagram, you can see the forming the carbocation is an endothermic step, and step 2 is the first with the low accretion energy. Now stereochemistry. You know the stereochemical evidence for the SN1 mechanism is less clear cut than it is for the SN2 mechanism. First order substitution do give complete racemization, may other do not. Typically there is a 5 to 20% inversion. So some of the product are not formed from free carbocations but rather from ions pair. So stereochemistry of SN1 reaction, you can see the planar intermediate should lead to loss of chirality. A free carbocation is a chiral and product should be raceme. Now role of ion pairs. You know, here is an intimate contact or tight ion pair, a loose or solvent separated ion pair, and the dissociation ion, each surrounded by the molecules of solvent, are formed. You know, the reactions product can result from attack by the nucleophile at any stage. Nucleophilic attack by solvent molecules on tight ion pair thus lead to the inversion attack on the solvent prepared ion pair, lead to racemizations. Look at here Rx substrate and then tight ion pair R plus X minus, then solvent separated ion pair and then separated. So formation of rearranged products, you can see the final products. So no substitution at bridge carbon. You know why? Not be the able to react by this mechanism, since the nucleophile requirement SN1 proceed through the carbocation, which must be planar. So reasons, what is the reason? Because of rigid cage-like structure, bridge head carbon atom cannot assume planarity. Hence the heterolysis leading to formations of carbocation is prevented. Now you know the SIT mechanism, single electron transfer. In some nucleophilic reaction, SN1 is highly probable. You know the ESR detection of intermediate free radicals are involved. Carbocation, good electron acceptor. The nucleophile, good electron donor. Mechanisms, single electron transfer mechanism. For example, the reactions between the triphenyl methyl cation and T-butoxide ion. In tert butoxide, you can see the products. So sometimes mix SN1 and SN2 mechanism. What does it mean? Some reactions of a given substrate undergo a given set of conditions display all the characteristic of SN1 in between two theories and SN2. So intermediate behavior and simultaneous operations. You know the SN2 simultaneous and SN1 intermediate. So intermediate behavior given by the SNIN mechanism that is neither pure SN1 nor pure SN2 but some in between type. All SN1 SN2 reaction can be accommodated by the basic mechanism, the ion pair mechanism. You know the substrate first ionizes to an intermediate ion pair that is then converted to products. So Rx, R plus, X minus and products. So given K2. So if a K1 greater than K2, then mechanism is SN2. If K2 greater than K1, then mechanism is SN1. So borderline behavior is found where the rates of formations of the destruction of the ion pair are of the same order of magnitude. K1 is equal to K2. Now simultaneous operation, no intermediate mechanism at all, and borderline behavior is caused by simultaneous operation in the same class of both the SN1 and SN2 mechanism, that is, some molecules react by SN1 and other react by SN2 mechanism. So among the experiments that have been cited for the viewpoint that borderline behavior results from simultaneous S1 SN2 mechanism in the behavior of 4-methoxybenzyl chloride in 70% equals acetone. So 4-methyl-methoxybenzyl chloride in 70% equals acetone. Conversion of 4-methoxybenzyl alcohol occurs by an SN1 mechanism. Alcohol is still a product but not 4-methoxybenzyl. Azide is another product. So increase the rate of ionization but decrease the rate of hydrolysis. So SN2 mechanism for azide formation when azide ion are added. So this is one case. So the SNI mechanism, you know the substitution nucleophilic internal. In a few reactions, nucleophilic substitution proceed with the retention of configuration even when there is no possibility of neighboring group participation effect. So follow the second order kinetics. That is rare the reaction between the alcohol and thionyl chloride has been studied exclusively. Examples, a phenyl alcohol and thionyl alcohol, you can see. It was found that product is formed with complete retention of configuration on the starting alcohol. The reaction proceeds with the formations of colorous sulfite ester which collapse with the elimination on sulfur dioxide. The colorous sulfite ester could form the product by SN2 with the inversion and SN1 with decimization. So, you know my friends, on the basis of experiment fact, the first step formation colorosulfite which is intermediate. Second step dissociation of the colorosulfite ester to form an ion pair, not dissociated. So because of the geometry of the ion pair, the chlorine atom is forced to attach the carbonium ion from the side as original CO bonds of the alcohol internal attack. So if 1-phenylethanol and thionyl chloride react in the presence of tertiary amines such as pyridine, the product is 1-phenylethyl chloride is obtained. That is, inversion of configuration occurs. The pyridine react with the HCl produced in the first step of the pyridinium hydrochloride is hydrochloric acid. Cl minus being an effective nucleophile attack the alkyl chlorosulfide from the back via SN2 reaction. So look at here the reaction scheme. Thus we can say in presence of pyridine, reactions follow the SN2 mechanism, without it follows the SN1 mechanism. So rate of reaction, both reactants plays crucial role in the reaction. Therefore, it is equal to ROH and thionyl chloride. So now nucleophilic substitution at allylic carbon. You know the allylic substrate rapidly undergo nucleophilic substitution reaction, usually accompanied by a certain kind of reagent known as allylic reagent. You know why allylic reagents are treated with the nucleophile under SN1 condition? Two products are usually obtained, the normal one and the reagent one. You can see here. So the reasons behind it, two products are formed because an allylic types of carbocation is an resonance hybrid, so that carbon 1 and carbon 3 each carry a partial positive charge and both are attacked by nucleophile, resulting in the formations of two products. So this mechanism has been called the SN1 prime mechanism. Now if equilibrium reach or not reach. If reach, stable product, thermodynamically controlled product. If less stable product, kinetically controlled product. So greater amounts and greater amounts. So there are two conditions. So nucleophilic substitution at allylic carbon can also take place by SN2 mechanism, in which case no allylic rearrangement usually takes place. So in which the nucleophile attack at the Y carbon rather than usual position, and this mechanism is called SN2 prime mechanism and is an allylic substitution. The SN2 prime mechanism takes place under SN2 condition where alpha substitution strictly retard the normal SN2 mechanisms. So you can see when a molecule has in an allylic position a nucleophilus means living group capable of giving the SNI reaction, it is possible for the nucleophile to attack at one Y position instead of the positions. This is called SNI prime mechanism and has been demonstrated on 2-butene-1-ol and 3-butene-2-ol, both of which gave 100% allylic rearrangement when treated with thionyl chloride in ether. Ordinary allylic rearrangement SN1 prime and SN2 prime mechanism could not be expected to give 100% rearrangement in both the cases. So, nucleophilic substitution at an aliphatic trigonal carbon. This is also very important topic. What does it mean? The compound containing a trigonal carbon, especially when the carbon is double bonded to an oxygen, a sulfur or nitrogen, undergo nucleophilic substitution through tetrahedral mechanism. Often reactions follows the second order called the addition elimination. So, in tetrahedral mechanism, first the nucleophile attract to give the tetrahedral intermediate and then the living group departs. So, as expected, this reaction is catalyzed by acid because protonation decrease the electron density at the carbon undergo substitution which facilitate the attack of nucleophile. Look at here. So, another important topic for you is nucleophilic substitution at a vinylic carbon. Concerned with the nucleophilic substitution at unsaturated carbon such as vinyl chloride, nucleophilic substitution at vinylic carbon is difficult under normal condition and is extremely slow compared to the substitution at the saturated carbon. The vinyl chlorides are essentially inert towards the nucleophile. What is the reason behind it? The reason is vinyl CX bond, X halogen, oxygen, nitrogen is stronger than alkyl CX bond because of the resonance interaction between the double bond and the unsaturated pair on X. This interaction also weakens the polarizes the pi bonds, which is why such compounds are reactive toward the electrophilic addition. So, the SN2 transition state as well as SN1 intermediate, a vinyl cation, are too high in energy to the really accessible. Look at here the scheme. It takes 16 to 18 calorically more energy to break the CX bond in the vinyl halide than the corresponding alkyl halide. Thus, the rate determining step involving the breaking of CX bond, the bond in vinyl halide is harder to break, the reaction is slow. So, after a lot of research, the vinyl cation and readily made through the solvolysis of the SN1 kind of the two condition are met. The living group is extremely good and vinylic group contains electron releasing substitution. So most commonly use of this purpose is super living groups, trifluoromethane sulfonate, which is known as triplet. You can see the vinylic triplet give vinylic cation and triplet anion. The powerful electron withdrawing F atom through dispersion of negative charge help to stabilize the triplet anion and makes the parent acid one of the strongest low boron state acid known, much stronger than known H2SO4 and perchlorate. So this is the reference advanced organic chemistry reaction mechanism and a structure by Jerry March, advanced organic chemistry by Jagdamba Singh, organic reaction and their mechanism P.S. Kalsi, reaction mechanism in organic chemistry S.M. Mukherjee. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel and thanks for watching.